Welcome back, everybody. So today we are talking about recharge and water divide. So in the last couple videos we studied a confined and then an unconfined aquifer at steady state, right? So there wasn't any recharge or there wasn't any time dependence. Here we want to look at an unconfined aquifer again, but this time we'll consider that there is rain coming in. So here at the top you can see the difference. So in the last lecture I told you, right, the maximum elevation of the water table was really at that higher head, side, and then you go down to the other one. When there is recharge, now we have a water divide here, which means that the water is flowing away from the divide and into the river, into both rivers, basically, for our example. So again, we start with, just like last time, right? We start with our normalized discharge per width of aquifer, write the Darcy's law, basically, and then crunch the number. Now, again, in the case of our last lecture, we said there wasn't any source or sink terms, basically, so dq prime dx was 0. Now, today, we do want a source term, which is that W or the rain on the landscape, and how does that change the equations? Okay, so let's look at this. So we start here at number 1 on the top left with that same equation, right, where dq prime dx equals something, rain. So again, this is in length per time, so this is millimeters per day, for example. Now again, replace q prime with its value, so that's the Darcy's law times the depth of the aquifer h. And again, like last time, we said we ended up with d squared h squared dx squared equals minus 2 w over k. Okay, so now again, that 2 comes from the equivalence here between h dh dx and half of dh squared dx squared. And so that 2 again is found on the other side, so it's just similar to what we've done before. Now once we have this equation here, we can solve this analytically just like before. We just integrate twice, right? We have d squared dx squared, so we do it twice and we end up with now a second degree polynomial, right? So again, remember in the last lecture for unconfined aquifer, the square of the head was linear in x, right? So now we have that new term here, which is our source term. So now we have a second degree polynomial in x, right? So we have a proper parabola. So h itself, of course, we can send that square on the other side, right? So h equals the square root of all this business. Again, we can use the boundaries to find the constants, right? Just like we did before. So this whole thing is going to be the same as last time, but now with the new source term, right? So if w is 0, right? If there's no recharge, we find the same exact equation as we had last time. Okay, but now with the W, with the wetness, now we have to account for the new term. Notice also that now our solution also depends on K, on the hydraulic conductivity. So how much the formation is letting water through, as well as the wetness. Okay, so now we can actually solve for, so the maximum, right, of the water table now is not, on the side, but it's somewhere in between, and that's what we call the divide. So to find the divide, oops, that should say q prime here, right? So the divide is located where q prime equals 0, so h max here, right, like I said before, now we have water flowing left and right. So this divide, the location of the divide, if you will, is the place where dh dx equals 0, or equivalently, or q prime equals 0, right? There's no flow, like, we're losing water both ways. So if we solve for dh dx equals 0, we can find where that divide is. At the top here we have the expression for q prime, right? And we're saying q prime equals 0 tells us where x is, right? So we can now solve for x equal, and you can see this is just, everything on the other side here, So x equal this value. This is our divide. So d divide equals this equation right here. So this is the water divide. Now for the example that we had in the previous lecture for the unconfined aquifer, you can see that we have the value of K. Of course, we have the two heads like before, so 5 meters and 375. So we can replace H1, H2, L was 500. So now we know K. And the only unknown from before was that W. So now we have W is 0.01. Which should be somewhere, but I didn't write it. But if we put W equals 0.01 meters per day, right, in the same units, or here, 0.01 meters per day, now we can put everything in, and we see that the divide is right at the midpoint. So the divide in this case would be exactly in the middle. Okay, so now we know where the divide is located. We can also calculate H max, right, the maximum elevation. So now we can just replace in the equation for H that we had before, this equation here. We know what the divide is. That's 250 meters, right in the middle for this example. So if we replace with the numbers that are given right here, we replace in with 250 and all the the parameters that are given. So you can see them here on the bottom with everything replaced, and you can see that the maximum head is 144 meters. Okay, so notice one thing, that this is a completely absurd number, right? Again, the river here is 5 meter head, so 144 meters is way high in the sky over there. So this just doesn't make any sense, right? That is that's like a whole hill, if you will. 140 meters above, that's 500 meters, 500 feet almost for those of you, or 400 for those of you speaking in feet. So that's literally a hill. So it doesn't work, right? Now the reason is because, again, K in the example given was very, very low, 0.03 meters per day. Remember that K should be in meters per day for a fine sand or something that's normally conducive. So 0.03 meters per day is a very low permeability formation, soil. The other side of that is the rain, right? The rain here is given as 0.01 meters per day. 0.01 meters per day is a lot of rain, right? So if you remember again from our first topic, the water cycle and water resources, remember that rain on land is about 800 millimeters per year. 800 millimeters per year, if you report that per day, right, divide that by 365 days, so 400, that's 2 millimeters per day, right, roughly. Now that's the total rain. So if you remember that 60-40 rule, so let's say take half of that for the runoff or the potential recharge to the groundwater. So you're talking about 1 millimeter per day as a rough estimate. And that's, of course, if you have all the runoff, right, go into the groundwater, which we know is not true, but even half of that. But again, order of magnitude, right, 1 millimeter per day might be a better estimate. So if we change K to 1 meter per day and W to 1 millimeters per day and rerun those calculations, you'll find that you get a head at the divide of 9 meters. So this is still, this is still quite a bit. Oh, and I can't. So 9 meters, right? So now it's going to be 9 meters, and I'm sorry I can't really erase in Keynote. So 9 meters is still, is still 4 meters higher than the level at the river. So that's still quite a bump, away from the river, but it's not, as dramatic as 144 meters. So that seems like a more reasonable, but still, if you have a river and let's say you're growing corn in your field, that, on a regular rain, your water table is actually going to be 4 meters higher than the river. That's quite a lot of, that's quite a bit that's quite a bit higher than the river. The other thing to note here is that the divide itself is at 240 meters, not 250, meaning now we're closer to that higher river. So we shifted the divide to the left, meaning we're fitting the boundary a little bit, right? So that that river now is contributing water, towards you. So you're not, right in the middle like before. So it was completely insensitive to, the rivers, but now you're actually filling the boundary a little bit. So you're not exactly in the middle. Okay, so this is it for today's lecture.